All right, ladies and gentlemen, today's class recording has started. So, yesterday we talked about some of the basics of atomic history, and we talked about how we developed the idea that matter is made out of atoms. And it starts with two competing theories. So, what are the two competing theories that kind of set the foundation for our description of what matter looks like? Eric, go ahead. Okay, so the theory, there's like 4 elements, and who put forth that theory? Aristotle. And then the other theory was put forth by who? Democritus, and what did he say? That everything's made up of atoms, and how do the atoms of different things compare to each other? Are they, like, if we take the atoms of this and the atoms of this, are they going to be the same? No. The atoms of this one are different than the atoms of this one, which is different than what Aristotle said, right? And so, while these are both theories, what did they lack? Evidence, right? Let's not go proof. That's kind of a like, you know, a weighted word, right? Evidence, okay? And then around the late 1700s, early 1800s, we get not necessarily a new theory, but an updated version of the atomic theory that was put forth by John Dalton, right? So basically, of the Aristotle theory or the Democritus theory, Dalton's theory is closer to which one? Democritus or Aristotle? Democritus, right? So Democritus basically had the idea, he just didn't have the evidence to back it up. Dalton, though, right, we talked about these different laws that came about in the 1700s, and he's got this evidence to back up what he's saying. And so Dalton says, all right, yep, stuff is made out of atoms. The atoms of one thing are different than the atoms of another thing. These atoms are indestructible. They're the smallest things out there. They don't have any electrical charge. Every atom of the same substance is the same, but every atom of different substances is different from one another, right? And then they can combine together, but when they do, they always do it, like it says, in whole number ratios, right? So you might get a ratio of 2 to 1 or 3 to 2, but you'll never find like half of an oxygen atom, or half of a carbon atom, or 3/4 of whatever, right? Always whole number ratios. Good there. Okay. There's a couple other people that are on your outline. We're going to skip over them, and we are going to fast forward to the bottom of your outline where it says J.D. Thomson and the cathode ray tube experiment. Okay? So I'm going to show you an awesomely lame video. Right? It only lasts like a minute, but it's like so awesomely lame that I just want you guys to watch it. So. Yes, that naturally they have no electric charge. And so, like, we haven't talked about electricity a whole lot yet. We'll talk about that later on. But I think most of you guys are aware of, like, positives and negatives, right? That there's positive charge and negative charge. Naturally, they don't have any electrical charge, but we will find that in reality, they become electrically charged, and that is the basis of what a lot of chemistry is. So we will get into that more as we go along. So yeah, these are like atoms in their natural states, all right? Like yeah, by themselves. Okay. All right. So let's check out this sweet video. And all right. Oh no. Okay. So check this out. Oh.
Such as this one. We need the Crookes tube that has a metal cathode, metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray. This stream of electrons illuminated. We can use a magnet to show the deflection of that stream. Here we can see the electrons being deflected by the magnet. The
cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
Sweet. Oh, right. That dude's goggles are pretty awesome too. He had like a suit and goggles on. That's always a good combination. So yeah. So, all right. So while that did explain the cathode ray tube, let's look at it in a little bit more detail. Okay. So these are some pictures that show the cathode ray tube, and up on the far right is sort of like in its basic state. Okay. So here's the deal. It's a glass tube, okay? Inside of the tube is that little white piece of paper, basically, okay? And you hook up a battery on either side of the glass tube. And when you hook up the battery on either side of the glass tube, you get this little green beam that looks kind of like a laser beam, okay? So like, oh cool, it creates laser beams. Except, if it was a laser beam, it would just be light, right? That's what lasers are, okay? But this green glowing beam, as you saw in the video, if you take a magnet, you can actually make the beam move. That's not what light does, right? Light, like you can't attract light to a magnet. Okay, it doesn't work that way. So that behavior, and also, never mind with that, it's okay. So with that behavior, people start realizing, hey, wait a second, this might not be what we think it is, all right? And so that leads us to J.J. Thomson and the cathode ray tube experiment, all right? I don't ask you guys to remember too many names in this class, but the four people that we're going to talk about, like Democritus, Dalton, and then now Thomson, and then one more, these are people you need to know, okay? So, J.J. Thomson and the cathode ray tube experiment. Just like we saw in the lame video that we just watched, right? That green glowing beam is either attracted or repelled by a magnet. And that means that it has some magnetic properties. It's not just light, okay? And we'll learn a little bit later on when we do our unit on electricity and magnetism. Electricity and magnetism are very closely related, so electrical things have magnetic properties. Based on the way the beam bends, right? We saw that one end of the magnet made it push away from the magnet, and the other end of the magnet made it come towards the magnet. Based on the way that the beam bends, when you bring the magnet close to it, Thomson realizes that that green beam of light is not a beam of light, it's a bunch of negatively charged particles. So that green beam of light is not light at all, it's glowing particles. And those particles have a negative charge. Okay? Good with that so far. Julia, go ahead. Okay. Here, 1897. Sorry, 1897. I think I have that on the next page. Okay. Yeah. 1897 for the cathode ray tube experiment. Okay? All right, so what does that do? Well, Joanna, like we said, Dalton said what about atoms and their electrical charge? They have no electrical charge. But here we're finding something that has an electrical charge. So what Thomson then kind of puts the pieces together and he says, okay, maybe atoms themselves aren't the smallest things out there. Because if there's a negatively charged thing, we can end up with no charge if we combine it together with something of positive charge. Does that make sense? If we put a negative and a positive together, we end up with nothing, right? So what Thomson realizes is, okay, these atoms that Dalton said existed aren't just the smallest solid pieces out there. They're actually made up of something smaller. And that's one of the smaller pieces that he refers, or that he gets, is these negatively charged things, which we now call electrons. Okay? So Thomson in the cathode ray tube experiment basically discovers the electron. Okay? Good with that for starters. All right. But Thomson has some evidence that takes Dalton's theory and makes it not true, right? Dalton said atoms were neutral and they are the smallest thing out there, but Thomson is like, that's not it. So if you have evidence that contradicts what a theory says, what do you have to do? Yes, but what do you do before you test it? Say again? You hypothesize and you come up with a new theory, right? So Thomson comes up with a new theory for what an atom looks like, and he calls it the plum pudding model. Okay? Most of you have probably never had plum pudding before. From what I can understand, I've never had it before. It's kind of like, has anybody ever had rice pudding before? With like raisins in it? I guess that's what it's kind of like. I always like to think of it this way. You know, Jello salad that like maybe your aunt makes at a picnic. The Jello that has like those little pieces of fruit in it. Like, you ever have like that before? It's like the little fruit that's like suspended in a big blob of Jello, right? You know, something like that. Okay. So here's what Thomson says. He goes, okay, Dalton said atoms were neutral. I have something that's negatively charged, so I'm pretty sure the atoms are not the smallest thing out there. So here's what he says. He says his little negatively charged electrons are the plums or the raisins in the plum pudding. Or if you want to think about it maybe as a chocolate chip cookie, the negatively charged particles are the chocolate chips. Okay? The rest of the cookie is the positive stuff that is canceling out the negatively chocolate chips and makes the cookie as a whole neutral. But if we can take the chips out of the cookie, they would be negative and the cookie would be positive. Is that okay as far as that goes? Are you okay with that? All right. So, 1897, Thomson does the cathode ray tube experiment and basically comes up with the idea that there are electrons, negatively charged particles, and he makes the atom look something like this. Okay? All right. Good there? Okay. Next, we come up to Rutherford's gold foil experiments. Okay? So, I'm going to tell you about Rutherford's gold foil experiment, and then I'm going to show you some things that sort of illustrate what it is. Okay? All right, first, a lot of times Rutherford gets credit for doing this experiment, but in actuality, two other guys, Geiger and Marsden, who were Rutherford's students, actually kind of did the experiment, and Rutherford just kind of like said, it was kind of like, I don't want to say he took credit for it, but he's like, you know, he was like their boss, basically. So, like, you know, when you do something for your boss, sometimes your boss gets credit for it, and you just kind of have to be like, yep, boss, good job, right? And so, anyway, but I'll give Geiger and Marsden a little bit of credit. So, most of you don't have to know that. You really have to just know Rutherford, but that's cool. So, okay, all right. Did you guys write down the description of the gold foil experiment? Okay. Go ahead and write this down. Which are A and B underneath Roman numeral letter V, all right, Roman numeral 5. So one spot above the picture and the other spot below the picture. All right, good so far? Okay with that? Okay. So let's take a look at a computer simulation that illustrates this. All right, we're going to start with this, okay? This is Rutherford's plum pudding model of the atom, okay? Let's say the reds are the electrons that are stuck in the white positively charged, right? So the red's are the chocolate chips, the white is the cookie, and they're just kind of like thrown in there, okay? All right. Over here, I have a gun that shoots something called alpha particles, okay? At the time, Rutherford doesn't even know what an alpha particle is. The only thing he knows about it is that it has a positive charge, okay? So, if I shoot something that has a positive charge at something that is made of a lot of positive charge, what should we see? When positives come close to positives, what happens?
Repel.
They repel, right? So, I'm going to turn on my gun, okay? All right? And that's what happens, right? Does that make sense? That all of these small pieces that have their own positive charge are all sort of bent away from the other positive charge. Good there? Okay? So, this is kind of what we would expect to happen to positive charges if we shot them at an atom, if it was what Thomson said it was. Okay? But Rutherford does this experiment, all right? And his experiment is set up something like this. Okay? You guys have this picture, so if you want to follow me. So over here on the left, a source of alpha particles. Like I said, Rutherford has no idea what an alpha particle is. He just knows it's positively charged. So he puts some stuff in a box, and he puts a little hole in the box, and the alpha particles shoot out of the hole, and now he's got a gun of alpha particles. And those alpha particles are positively charged. Okay? Right in the middle, there is a little piece of gold foil. Just like the aluminum foil that you have in your kitchen, except it's made out of gold instead of aluminum. Okay? Good so far? All right. Why gold? It's a lot bigger than aluminum. All right? We know that gold atoms are much bigger than aluminum atoms at the top. Okay? And then he's got a big cardboard screen that sort of surrounds the gold foil. And it's coated with the same kind of material that glows in the cathode ray tube. All right? The material in the cathode ray tube only glowed when those negatively charged particles hit it. Okay? This will only glow if something has a charge and hits it. All right? So he turns on his alpha particle gun and shoots it at this gold foil, and here's what he finds. There's a big, bright spot that shows up directly behind the gold foil. As if all of those alpha particles went right through the gold foil and didn't hit anything. Which is completely contradictory to this, right? If we shot a bunch of alpha particles at an entire sheet of atoms, nothing would get through them, right? Right? But here we see a bunch of them are getting through. Weird. So, this is what Rutherford figures out. Okay? Yeah, can you guys see that, or do I need to turn the lights off? I'll turn them off. Okay. So, the purple ones are the alpha particles. They look a little different in this simulation than they do in the other simulation. Okay? So we see that some of them hit the little yellow dots, but some of them just go straight through and don't hit anything. You guys see? Do you see that as far as how this works? Right? Yeah. So unlike the first simulation where all of them got bent away from this positively charged atom, here only a few of them are getting bent away. Okay? So here's what Rutherford realizes. That atom that we thought was solid really isn't solid. And most of it is empty space because all of these purple ones just kind of go straight through and they don't run into anything. But every once in a while, we find one that kind of bumps to the side and gets sort of like shot off at an angle. So he realizes, oh, it must be hitting something. There's just not a lot of those somethings to hit. Okay? And so he puts all of this together, all of this idea together, and he comes up with this as far as an atom. Okay? Unlike the chocolate chip cookie that J.J. Thomson thought an atom was, Rutherford realizes that an atom is mostly empty space. And it has a real small, tiny, but very dense part in the middle that's called the nucleus. The nucleus has almost all of the mass of the atom. But it only takes up a very small space or volume of the atom. And that the electrons are outside of the nucleus, and that the nucleus has a positive charge. How did he know? Well, positively charged alpha particles, some of them are being bent around, but most of them just go straight. Okay? So he comes up with this idea of the atom having a nucleus. Okay? And so we go from this, okay? Well, let's do this. Okay? If you asked Dalton, you guys might want to make a little drawing down at the bottom of your outline. If you asked Dalton what an atom looked like, what would he tell you? Nope, that's Thomson. If you asked Dalton what an atom looked like, what would he tell you? What did Dalton say about atoms? They're identical. They're indestructible, right? So if you asked Dalton what an atom looked like, he would tell you it looks like this. Boom. A solid circle. Nothing inside of it. Does that make sense? Okay? Because that's what Dalton thought an atom looked like. That it didn't have any parts. It was the smallest thing out there. So it's just a solid circle. Or a sphere, if you want to think of it that way. Right? Alright, so this is your Dalton atom. Okay? Alright. Chris, what did Rutherford say? That's plum pudding, right? So, here, but... Nope. Yeah, well, yes, but Thomson is plum pudding, right? Now we're doing Thomson. Did I say Rutherford? Yeah. My bad, sorry. Dalton here, okay, because this was like the earliest one, right? Thomson's next, and this is plum pudding, right? What do the little yellow dots represent? Nope. The electrons. Those are the negatively charged ones, right? Okay? So Thomson has an atom here, right? I should label this as Thomson. Okay. Alright. And Chris, what do we call this one? Plum pudding. And, like we said, those little yellow dots, those are electrons. Good? Alright, good there? And then the little black stuff around the outside, that would be just like the positive stuff. It's just kind of a gooey mess that has little negative stuff stuck in there. Okay? But then, what does Rutherford do to all the positive stuff? He brings it all together where? In the nucleus, right? And the nucleus is really small. Right? So now we have a really small nucleus right here, and then the electrons just kind of float around the outside of it. Right? Does that make sense? Right? And then this would be our Rutherford atom. All right. We okay with that as far as a timeline of, oh, Rutherford is like early 1900s, 1905-ish, between 1905 and 1910, okay? So we go from a really, really long time of nothing, right, all the way from Democritus to Dalton, and then from Dalton to Thomson's about 100 years, and then from Thomson to Rutherford is about, like 10 years, okay? So we're starting to get some developments real quick, okay? All right, good there. Okay, so let's talk about, now that we have a picture of what an atom looks like, let's talk about how we differ atoms one from the other, okay? So let's start the new outline that I gave you today. Let's talk about atomic structure. Because I know that sounds like exciting, right? Atomic structure, totally. Yep. Sorry, buddy. This is, admittedly, this is not my favorite stuff to teach. I'm just throwing it out there, but I've got to like go through it because it leads to more exciting things. So. All right. So an atom. An atom is the smallest particle of an element that retains the properties of that element. Okay? They are not the smallest things out there, but if you take an atom apart, you don't have gold anymore, or you don't have oxygen anymore, or you don't have hydrogen anymore. Okay? The atom is the smallest particle that retains the properties of that element. Okay? And like I said, when it says properties, mostly those are chemical properties, but not physical properties. But through the work of Thomson and Rutherford and another guy named James Chadwick, who we didn't talk about there, okay, we get the idea, or we figure out that there are these things called subatomic particles. And because you know English, you could probably tell me what a subatomic particle is, right? If we throw sub on something, what does that mean? Smaller, or less than, or below, right? So subatomic particles are things that are smaller than atoms, right? Particles of matter that make up atoms. These subatomic particles are smaller than the atoms themselves and behave differently than whole atoms do. And I'm guessing that you guys probably know the big three as far as subatomic particles are concerned, right? Are you assuming we know three subatomic particles? No? They are protons, neutrons, and electrons, okay? Just so you guys know, there are way more subatomic particles than protons, neutrons, and electrons. We're not going to learn about them in this class because they get really, really weird, all right? So you know. It's like the best I can describe. It's just weird, like that they behave really different. They behave real weird, and they're like really small and hard to like create and stuff like that. They're called quarks and leptons and like it's stuff. So you get physics that when you get into like atomic physics and stuff like that, that's when you start learning about that. So it's actually kind of cool, but it's so weird. You're like, this is just weird. And so, yeah. But the evidence suggests that that's what's happening. So let's talk about the big three, though. Okay. All right. Protons. Okay. Protons have a positive charge, and they are found in the nucleus of the atom. As far as you're concerned, atoms are going to be made up of three pieces: protons, neutrons, and electrons. But just so you know, there's more stuff out there than that. Protons, positively charged particles found in the nucleus of the atom. Okay? Good there? Next, neutrons. Particles that have no charge, and they are also found in the nucleus of the atom. And then finally, electrons. Electrons have negative charge, and they are found outside of the nucleus in an area that we call the electron cloud. And we'll learn a lot more about the electron cloud next week when we talk about the quantum mechanical model of the atom. All right, good there? All right, okay, so let's talk about the nucleus. Rutherford's experiment told us a bunch of things about the nucleus. What does Rutherford's experiment tell us about the nucleus of the atom? It's small. Okay, what else? It has a lot of mass, but not a lot of what? It has a lot of mass, but how big is it? Small. So it has a lot of mass, but not a lot of volume. Okay? It's small, a lot of mass, not a lot of volume. What else? There's one more thing about the nucleus that's important. Positively charged. All right? So, central core of the atom. It's composed of protons and neutrons. And that means overall it has a positive charge. Because protons have positive charge, neutrons don't have any charge, and so we end up with a positive charge overall. Okay. Now, if you know anything about charges, which I think you guys know a little bit about, right? If you put two positive charges together, what do they try to do to each other? They try to repel each other. So, if you have a bunch of protons that all have positive charge in a real small space, what are they going to do? They're going to try and repel each other. So, the nucleus shouldn't stay together on its own, but it does. And that means that something is holding them all together. And that something is we call the strong nuclear force. It's a force, just like we talked about in the first part. It makes things accelerate, or it holds them in equilibrium, right? So all these protons are in equilibrium. The repulsion from the other protons pushing out, the strong nuclear force pulling in, and it holds them in place. The weak nuclear force, electrostatics, which is positives and negatives, and gravity. Okay. Those are the four forces that we know about that exist. And when you get into particle physics, you learn about those forces and what they are. Again, weirdness. So, okay. All right. It contains almost all of the mass of the atom. It is very, very dense because it is a very small percentage of the volume of the atom. Okay? Good there? Sorry, very small percentage of the volume of the atom, so if you filled that in, you heard me talk about it. I know some of you just don't listen to me, just right, it's on the screen, that's cool. And finally, I think there's one more question that we have there, right? So, as the nucleus of the atom gets bigger and bigger and bigger, it becomes more difficult to create and unstable. Why? Got to push all those protons together. And the more and more protons that we have, what is there more and more of? There's more repelling. There's more repulsion, right? So if you look at the percentage of what kind of elements show up in the universe, big ones don't show up very often. Why? Because they're really hard to make. You can't push all those protons together, right? So as it gets bigger and bigger and bigger, it becomes more difficult to create and more unstable. Why? Because the more protons we have, the more repulsion we have. I wouldn't say it's a direct relation, like Julie, it's not necessarily like mathematically a direct relationship, but just like, yeah, more protons, more repulsion, that is a direct relationship, but that leads to then bigger nuclei being harder to make. Yeah, but not necessarily like a direct relationship, like not a straight line on a graph direct relationship. All right, how's that? Let's call it a day there. Tomorrow we'll start getting into telling how many protons are in an atom, and we'll do a little bit of quick math, like some addition and subtraction kind of stuff, and we'll tell one atom apart from another atom. So.
Physics your senior year?